All right, so we'll cover chapters 9 and 10. And this is on categorical data. Okay, so we're going to handle inference and hypothesis tests for categorical data. So we're going to start off with just the simplest case, which is, can we make inference about a proportion in a population? Okay, so we're going to do for a proportion in a population. So anytime you've got categorical data, your data is going to be recorded in either counts. Well, most likely the raw data will be recorded with counts. How many people in the population are female, how many people in the population have had a heart attack or whatever it might be. Okay, how many people have this? And then we often turn those counts into proportions. So what we're going to do is we're going to do inference for a proportion in a population. Okay, so we're going to do a confidence interval for P based on a sample. Okay, so P is equal to the population proportion. So you have learned how to make a confidence interval for mu based on a sample, which would be this population mean. And we're going to do confidence interval for P, the population proportion. Okay. What did the confidence interval for the mean look like? Review. So CI for mu looks like what goes in the middle? Y bar plus or minus T star times the standard error of Y bar? Is that yes? Okay, and so this can be this is kind of the formula. We can just say our current estimate plus or minus a critical value times the standard error. Okay, and so when we create a confidence interval for P, it's going to have the same form. Estimate plus or minus critical value times the standard error. Okay. So I'm going to just I'm going to put what's known as the classical confidence interval, but this is not what's covered in the book, and so I'll do the method covered in the book, and I'll kind of try to explain the difference between your classical, well, maybe not classical is the right word, the traditional. Okay, so this is a quote traditional confidence interval for P. This is going to be the estimate P hat, your sample proportion, plus or minus 95% confidence interval will be 1.96 times the standard error, which is P hat times 1 minus P hat over n. Okay? Where p hat is equal to, you know, y over n. So the number of females divided by the total size of the population, or whatever it might be, whatever your y is. The number of people with brown hair divided by the total people in the population, something like that. Okay? Our book uses p tilde or p squiggle rather than p hat. Okay? Okay, and this is the Wilson adjusted proportion. And what this is equal to is equal to y plus 2 divided by n plus 4. Okay? And what this does is it kind of it helps in situations, in extreme situations. So let's say you wanted to know what proportion of people have 11 fingers, or something like this, okay? And some people are born with 11 fingers, but it's very rare, okay? And so you might survey 100 people or 200 people, and 0 out of your 200 people that you surveyed have 11 fingers, okay? And in that case, your adjusted your proportion would be 0 divided by 200. Your p hat is 0, okay? And if your p hat is 0, then your standard error is going to be 0 times 1 over n. This is also going to be 0, okay? Because when you have a proportion of 0, you've got no standard error here, okay? And so what the Wilson adjusted proportion does is it says, we're going to pretend like we saw 2. Okay, it just throws in a 2. So it just kind of takes it away from that 0. Okay? And then to kind of compensate, it also sticks on 4 on the bottom. And this also has the opposite effect when you're in the extreme proportions where your sample's likely to be 100%. So if you said, what proportion of people have 10 fingers, maybe you surveyed 50 people, and all 50 people that you surveyed have 10 fingers. So in that case, your p hat would be 1, and again, you would have no standard error. But what this does, it says, okay, if you saw 50 out of 50, what we're going to do is we're going to add 2 to the numerator and 2 to the denominator, and we'll have 52 out of 54. Okay? So this kind of forces you to observe 2 yeses and also 2 nos out of 4 additional. Okay, so kind of it fudges the number on purpose. Okay, so p tilde p squiggle is the Wilson adjusted proportion, and then so our confidence interval for p, okay, based on the Wilson adjusted proportion is going to be p squiggle plus or minus 1.96 times the square root of n plus 4. Okay, and that's basically it. You just plug in the numbers you have. You take the data from your sample, you plug it in here, and you get some kind of confidence interval. So let's say you create a confidence interval, And I'm hoping at this point you're comfortable with the language behind a confidence interval. I graded some of the labs. I haven't graded them all, but it seems like most of you have got it down when they ask, what does it mean to be 95% confident? The labs I read had good answers, saying things like, you know, if we were to repeatedly take multiple confidence intervals, we would expect about 95% of these to capture the true value of the population. And you know, we say, you know, we're 95% confident about this and that. So, you know, let's say, you know, if our CI is 0.47 to 0.55, okay, we would say I am 95% confident that the proportion of people in the population who blah 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 is between 0.47 and 0.55. Is that okay? I think this part, so far so good. If I asked, okay, what if this was a confidence interval for people who are going to vote yes on proposition XYZ? Do we have evidence that proposition XYZ will pass? No, why not? Oh, I mean, so, you know, let's say our survey was, we surveyed people, we took a random survey and we said, are you going to vote yes for proposition XYZ? And then, you know, this proportion said yes. And we did the confidence interval and we got 47 to 50, 0.47 to 0.55. And we're saying I'm 95% confident that the proportion of people in the population who, in this case, who will vote for XYZ is between 0.47 and 0.55. So, do we have evidence that over half the people support XYZ? What do you think? Okay, so you're saying no, and why not?
Well, because it could be anywhere from 0.47, which would be less than half.
Yeah, so yeah, because 0.50, because half, 0.5 is in here, and you know it could be between 0.47 to 0.499999. We don't have evidence that the proposition will pass with a majority. Okay. So I'm 95% confident. So in this case, we would say I do not have evidence. If there was the question, we would answer it with I do not have evidence that over half the people blah 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 dot 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 support XYZ, or over half the people, I don't know, whatever it is, have brown hair or eat hot dogs. Okay, is that all right? Confidence intervals. So I think this is pretty easy and straightforward, especially because we've had exposure to confidence intervals already. It's the exact same idea, and it's just being applied to proportion. Okay. All right. So let's. We're going to now do inference, hypothesis test for proportions. And this brings us to what's known as the Chi-Squared tests. Okay, so we have hypothesis tests. proportions, okay, and this family is called the Chi-Squared tests. So it looks like an X, but it's pronounced chi. Chi-squared tests, not chi. That's the trouble with English. We have the same set of letters, and they are pronounced different ways. Okay. What is that called in English? So in homophones are two words that have different spellings but sound the same. What is it when it's two words that have the same spelling but homonym? Okay. All right. Yes, so homonyms, chi and chi and whatever else, present and present. I think I was talking to, it doesn't matter. I talked to somebody and he kept saying, I want to give you a present. And I had no idea what he was talking about. I was like, what? But, it's just because he was just pronouncing it wrong, and it's not his fault, just, it's our language, right? Okay. All right, so we have two chi-squared tests. We have the chi-squared goodness of fit test, and this is covered in chapter 9, and I don't know, maybe our book felt like it would be too long of a chapter, but I think they just go hand in hand with the chi-squared chi-squared test for independence. And this is covered in chapter 10. Okay? And so the difference between the goodness of fit test and the test for independence, okay? So I'm going to just write GOF for goodness of fit test. Here we are looking at just one categorical variable. Okay? And we have certain proportions in mind. And our test, and then we have data. Okay, and our test says how well is the fit? How well do these proportions that we have in mind fit the data we see? Okay, or how good is the fit? And so we have the goodness of fit, although. Is goodness the right word? Yeah, okay, so it's really how well does the proportions we have fit the data, okay, and we ask how well do the proportions we have in mind, have in mind, fit the data we see. Okay. And basically our test statistic measures basically the discrepancy between our data and what we would expect if our proportions were correct. Okay. And so if the discrepancy between our data and and what we would expect under our proportions is very small, then we have no reason to doubt the proportions we have in mind. On the other hand, if the discrepancy between what we observe and what we expected is large, then we have reason to suspect that our proportions are wrong. Okay? The chi-squared test for independence is very similar. Except we now have two categorical variables. Okay, and the proportions we have in mind are determined by the probability rules regarding independence. Okay. By the rules of probability. Specifically the ones for rules about independence. Okay, and then we ask this question: how well do the proportions we have in mind fit the data we see? And our test statistic measures the discrepancy between the data and what we expect if things were independent. Okay. How well do our proportions fit the data? And we measure this discrepancy. Okay, so that's conceptually kind of the big picture ideas behind the chi-squared tests. We have proportions in mind, and we want to say, hey, the data we observe, our categorical data, do they fit the proportions we have in mind? Or I guess it should be the other way. Do the proportions we have in mind fit the data that we observed? And if there's not a whole lot of discrepancy between what we see here and what we see and what we expected, we got no reason to doubt these proportions. On the other hand, maybe we do. Okay, so if someone says something like, half the people at UCLA are female and the other half are male, maybe you take a survey. You take a random sample, maybe you select 100 people. You happened, in this random selection of 100 people, 52 are female and 48 are male. Okay, that's not exactly half and half, but is that discrepancy big? Not really. Okay, so in that case, the discrepancy is small, so you have no really, this is just kind of, we'll do all the math behind this, but you have no reason to doubt that that the claim of half female, half male is wrong. Okay. On the other hand, if maybe somebody said half the people in the military are female and half are male. Okay, and so maybe you take a random sample of people from the military. Okay, you take 100 people. And when you select 100 people, maybe 82 are male and 18 are female. Okay? So if that claim was true, we would have expected about 50 male and 50 female. What we're observing is 82 and 18. So in that case, the discrepancy seems large, and we would say we have our data causes us to believe that this original claim is wrong. Okay? And that's essentially what we're doing. We just kind of beef it up with the mathematical calculation of statistics, and there's an underlying distribution known as the chi-squared distribution that determines all of this, which, believe it or not, when you look at it, you won't believe that it is based on the central limit theorem, but it is. So, we'll get into the grit of the test itself. Okay, so let's say so someone claims half of students at UCLA are female and half are male. Okay? And so in this case, our null hypothesis is going to be written this way. The proportion female, or there's a few ways we can write it. Okay, we can write probability of selecting female is equal to 0.5, and the probability of selecting a male is equal to 0.5. Okay, and then the alternative hypothesis would be basically it's always the same. At least one of the proportions in our null hypothesis is wrong. Now in this case, because there's only two proportions, if the female one is wrong, then that necessitates that the male one is wrong. Okay? But you could have a scenario where you have 3 proportions or 4 proportions, and if one of them is wrong, it could mean that all of the other ones are also wrong, or it could also mean that just one is wrong, but the other ones are like it gets absorbed in some of the other ones. And so, so when it's written this way, this is just this is a non-directional alternative. I'll cover the scenario case where we have a directional alternative as well. Okay, so let's say you go around, and this is our data. Okay, 100 people surveyed. Okay, and then here's the results. Female, we have 52. Male, we have 48. Okay? And so this is our data, and what we have to do is we have to create expected counts if null hypothesis correct. Okay, so if the null hypothesis were correct, what would be the expected counts? Okay, so the expected counts would be 100 times 0.5. We would expect 50 to be female, and 50 to be male. Okay, and we measure this discrepancy using the Chi-Squared Statistic. So the Chi-Squared Statistic is calculated as observed minus expected squared divided by expected. Okay, and we add this up for all categories. Okay, sum for all categories. Okay, so in our case, our Chi-Squared Statistic would be, we observed 52 females, we're expecting 50, so we square that difference, divide by our expected number. Over here we have 48 minus 50, we square that difference, divide by 50, and we add those two together. So what do I have? Six. What? 0.16. It's really small. Okay. Is that okay? So my Chi-Squared Statistic is 0.16. We're going to look this up in the Chi-Squared table. The degrees of freedom is equal to the number of categories minus 1. So we have 2 categories, male and female. We have 1 degree of freedom. Okay, so we're going to look up 0.16 with 1 degree of freedom. We go to the Chi-Squared table, okay? And what do we see? Let me just copy this. So looking at just that top row for 1 degree of freedom, we're looking for this value 0.16, and we see 0.16 goes right here, so our tail area, whatever it is, it's going to be much greater than 20%. Okay. The Chi-Squared table says our tail areas are for non-directional alternatives. Okay. If the alternative is directional, which is actually only possible when the degrees of freedom is equal to 1, the p-values are found by taking the column headings and dividing by 2. Okay, so in our case, our p-value is greater than 20%. Okay, if we use alpha equal to 5%, we do not reject the null hypothesis. And we say we have no evidence that the proportion of, females and males at UCLA being 0.5, that the proportions, I'll just say that the proportions in the null hypothesis are wrong. Okay. And this can be applied, if you have 5 categories or 4 categories, you just do the same thing. You just take your n and you multiply it by the p that exists for each category to get your expected count if the null hypothesis is true. And then I just lost my train of thought. Yeah, so you do it for each category, and then you calculate your Chi-Squared statistic, look it up in the table, and that's it. Okay. There is a so the Chi-Squared table, the Chi-Squared distribution, is based on the distribution of random variables if you take a random normal variable and you were to square it. Okay. And so it's a little bit odd. We're not going to cover the derivation of it. And all of the math behind this, there is kind of a central limit theorem underlying assumption. And so we do have what we call, there's one condition that we have to check, and that is to make sure the combination of sample size and proportions are big enough. Okay, so we do have just one condition. Well, 2 conditions. One is that the data have to be selected randomly and independently. And that applies to all hypothesis tests. So even the non-parametric ones requires that our data be selected randomly. Okay? You don't have to, non-parametric tests don't put any assumptions about the distribution of data, but pretty much all hypothesis tests require that they be selected randomly. Otherwise, everything falls apart. Okay, so one condition other than random and independent is that the expected counts for all categories all of the categories have to be at least 5. Okay, and then depending on the textbook, some other textbooks might say it should be 7 or it should be 10 or something. Okay. And if they're not at least 5, then you have a few choices. Okay, so if this condition is not met, there is a non-parametric test called Fisher's exact test, which we are not covering. That can be used. And then the other one is to combine categories so that all the categories are over 5. Okay, so 2 options if this condition is not met. Okay, so 1, Fisher's exact test. Okay, and this is non-parametric. Or combine categories. So, so all categories are at least 5. All right, so just a simple example. Let's say your null hypothesis, we have things like the probability that someone has, we'll say blonde hair, brown hair, black hair, red hair, and other color hair. Okay, and so let's say, I'm just making up numbers here, I have no idea. This is, if we do it for America, this is too much here. I think that adds up. Okay. And let's say you take a sample of 50 people. Okay. And then so you have your data, and you have blonde, brown, black, red, and other color hair. And it's or actually this is too small anyway. Let's do 100. Okay. And so you have your whatever, your counts. I don't feel like doing this. Okay. So you have your data, and then you also have your expected counts. Okay. And the expected counts for each of these categories will be 20, with 100 people will be 20, 40, 32, 5, and 3. Okay? So this one is not big enough because it's not at least 5. So you would then combine these two together, the red and the other. And so you would have to then change this. So, so now you have probability of red and other equal to 0.08. You combine your data as such, and then so your expected counts will be the same, except now you have red and other equal to 8. Does that make sense? Okay, kind of. So after you redo it, blonde, brown, black. So these would all be the same as before. But now you have combined red and other together into one. Okay? How many degrees of freedom would we have in this test? 3. Okay? So now that we have revised, so we have to revise our null hypothesis. Okay? So all of this is the same as before. At least these 3. These 3 are the same as before. Whoops. So those are the same as before. So we have 4 categories here. So our degrees of freedom would be 4 minus 1, we have 3 degrees of freedom, okay? And then the chi-squared, we just take our observed data, you know, same thing as before. Observed minus expected, quantity squared over expected. Add them up, divide by, just add them up. And then you look that up in your chi-squared table with n minus 1 degrees of freedom. Are there questions about that? No? Okay. Let's do, we'll do one example where we have a directional alternative. And this will be chi-squared goodness of fit. Okay, and so let's say someone claims the null hypothesis is, you know, probability of female in the military is 0.5, okay? And then someone says, no, there's no way that can be right. The probability of females in the military is less than 0.5, okay? And notice, because we're, in this case, we're just going to kind of simplify this and just say people are either female or they're not female. I don't have to necessarily write the other categories here, okay? So in this case, we're just kind of simplifying it to just say there are females and there are those who are not female, okay? So, I mean, for all intents and purposes, that would be female or male. But I guess to be specific, we'll say female and not female, okay? I don't know what the military provision is for transgender people. I don't know if I don't know what happens. Like, are they? Does anyone know? Are they? I don't want to use the word allowed, but like, does the military make any kind of accommodations for that? I have no idea. I know Bradley or Chelsea Manning, but I don't. That's like, it's different because he's or she's in jail now or court-martialed and everything. So I don't know. It's a good question. Okay. Anyway, let's say you go through this and you collect data, and you have so the 100 people that you surveyed, and the number of females, 18. Okay, so which means non-females would be 82, right? Okay. If the null hypothesis were true, our expected values would be females 50 and non-females 50. Well, I guess because we haven't heard anything in the news about the military and transgender, I'm going to assume that they are not accommodated for. Okay, so we just do this difference. We do 18 minus 50 quantity squared over 50 plus 82 minus 50 squared over 50. What is this? 18 minus 50 is 32. 32 squared is 1024. That is big number. Okay, so we get 20.48, and this one will also be 20.48. It's not always, I know in both of the examples, because the expected numbers were 50 in 15 we had 1 degree of freedom, it happened to be 20.48 plus 20.48. That's not always the case, okay? It's just a coincidence that in my two examples that I did, it happened to be this way. So anyway, our chi-squared statistic is 40.96. We look this up with 1 degree of freedom. So, our table goes up to 15.14 and it says it's 0.0001. So we would get our p-value, our tail area is going to be less than 0.0001. This is for a non-directional. So for a directional alternative, what would our p-value be? Our p-value would then be half of this. So it's less than 4 zeros and a 5. Okay, and so this means we reject the null hypothesis. We have evidence that the US military is less than 50% female. I wonder if any nation's military is close to being 50% female. I think Israel has a very high proportion of females in the military compared to other nations, but I still don't think it's 50%. So, okay. Is that good? Okay, and so the next application of the the chi-squared test is to test to see if two categorical variables are independent. Okay, and so the book moves all of this stuff into chapter 10, but I feel like it fits in with chapter 9. Okay. All right, so the chi-squared test for independence, we look at two categorical variables. And we see if they are independent. Okay, and so in okay, so if we have, let's just review what we remember from probability. We have two events, A and B. Let's say if A and B are independent, then the probability of A and B is equal to, do you guys remember? Probability of A times the probability of B. Okay? So, if flipping the coin the first time has a probability of 0.5 landing heads, and the probability that it flips on heads is 0.5 for the second one because they're independent, then the probability that we will get 2 heads is going to be 0.5 times 0.5, 0.25. Okay? All right, and so let's just try a scenario here where we would expect things to be independent, okay? Okay, so we'll say, is wearing glasses independent of being left-handed. Okay, and so we will say our null hypothesis. Okay, so if we write it out in words, will just be wearing glasses is independent of being left-handed. Okay, or symbolically, we could write probability of wearing glasses given left-handed is equal to the probability of wearing glasses what? Period. Okay? Or, you know, we could write it, there's a few ways we could write this. Probability of wearing glasses if you're right-handed, or probability of glasses, period. Okay, so any of these, any combination of these would be fine as the null hypothesis. Okay, and we're going to just, well, I guess in this case we'll say you're either left-handed or you're right-handed. Okay, and I know that's not always the case, but we'll just simplify our world and say you either are left-handed or right-handed. Okay, and then the alternative will then be, we'll start off with a non-directional alternative. We'll say probability of glasses given left-handed is not equal to the probability of glasses given right-handed. All right, and let's say we gather data. Okay, so this is our data. So we'll say glasses, and we'll have no glasses. And we'll have left-handed versus right-handed. Okay, so let's put 10 here, 70 here, and 15 and 100. So what is this? This is 25, 170, 80, 115. Oh, am I adding something up wrong? Oh, no, I'm not. 195. Okay. My brain just got stuck for a second. Okay, so this is what our data is, okay? This is what we observed. Okay. Now, I suppose, so I wrote this out in a nice two-way table, but the data could be presented in kind of paragraph form, right? The data could be presented in saying, like, after surveying 195 people, you found that 25 were left-handed and 170 were right-handed. Of the left-handed people, 10 of them wore glasses and 15 did not, or something like that. You know, it could be written out in paragraph form, and then you'd have to say, well, what does this look like in a table? Okay, so make yourself a two-way table here. Okay. All right, so let's talk about what we would expect. So let's see. I'm going to copy this table onto the next slide just because I want a little bit more space to work with here. Okay. So this is our observed data. Okay, and let's talk about what we would expect. So keep in mind our probability rule, right? So the probability rule was that probability of A and B is going to equal the probability of A times the probability of B. Okay? So empirically, what is our empirical probability of wearing glasses? So we're going to create our expected table down here. But empirically, what is the probability of wearing glasses? (80 over 195, right? This is our empirical probability of wearing glasses. Okay. And what is the probability of being left-handed? (25 over 195. Okay. And then, so what would the, so if A and B were independent, what would the probability of being left-handed and wearing glasses be? Well, I would multiply these two together, right? I would do 25 over 195 times 80 over 195. Is that okay? So this is what we would expect. This is the expected probability if null hypothesis were true. Okay, or expected probability if A and B are independent. Okay, so let's create our expected table. Okay, so I've got glasses, no glasses, left hand and right hand. Okay, so the expected probability of ending up in this square is going to be 25 over 195 times 80 over 195. Okay. But that's the probability. What would our expected count be? I should multiply this probability by what? By how many people I've surveyed, right? So how many people did I survey? 195. Is that okay? So my expected count will be 195 times this probability, which is 25 over 195 times 80 over 195. Is that okay with everybody? Okay, and so we're just going to punch this out in our calculator. I do 195 times 20 divided by 195 times 80 divided by 195. Okay, and so I get an expected count of 8.205. And it's totally fine that my expected count has a decimal. Okay? Yes, question. Did I do 20? Oh, yeah. I didn't mean to do that. So don't write 8.205 because I messed that up. 25 divided by 195. Okay. 195 times 25 over 195 plus 80 over, okay, thank you. Okay, so my expected count is 10.256. We're going to have pathetically small chi-squared statistic. Well, that's fine. Okay, so my expected count is 10.256. It's totally fine that there's a decimal. Keep the decimal, don't throw those away. You need them. Okay, and then we can go through the same process to figure out all of the other cells, okay? And so this one would be what? 195 times 170 over 195 times 80 over 195, right? But there's another thing. We can say, well, if this is 10.256, and we're going to just say our row adds up to 80, we know that this must be 80 minus 10.256. Okay, so I can just do 80 minus this, and I get 69.745. Okay, and if this and this have to add up to 25, then I know this has to be 14 point, oops, this should be 744. Sorry. 744. And if these two have to add up together, then this should be 100.256. Is that okay? So the expected count is equal to n times the row total divided by n times column total divided by n, okay? Or we can cancel out the n's and we can just say the expected count is row total times column total divided by n, which is our grand total. Okay, and you can use this to calculate each square, or you can just calculate it for one, and then knowing that the rows and the columns have to add up, just figure them out that way, okay? And so this actually illustrates one interesting thing, is that the degrees of freedom when you have a two-way table is not n minus 1, it's the number of columns minus 1 times the number of rows minus 1. So in our case, we have 2 columns minus 1 and 2 rows minus 1. So we have 1 times 1, we have 1 degree of freedom. Okay, so in our table, we have 1 degree of freedom, and we kind of see that in that as soon as one number was determined, the other numbers were kind of locked down. They had no freedom per se. They couldn't. If this is 10.256, this has no other choice than to be this number. Okay, so there's one thing there. Okay, is this okay? And so now we have our observed counts, our observed data, and our expected table, and then we can go through and calculate the Chi-Squared Statistic. All right, so I'm going to just copy these tables onto the next slide. You obviously don't have to recopy them. So we're going to use these to get our Chi-Squared Statistic. So the Chi-Squared Statistic, again, measures the discrepancy between what we observed and what we expected. And so we do 10 minus 10.256 squared over 10.256 plus, and the order, it doesn't matter because we're adding them all up. this? 15 minus. So one interesting thing is that if you have 1 degree of freedom, the numerators, only the numerators, end up being the same. And that's only if you have 1 degree of freedom. Okay, so in our case, our numerators are all going to be 0.256 quantity squared. The denominators are all different. Okay, but anyway, we do this and we get a chi-squared statistic. It's going to be fantastically small, but I'll go ahead and do the math here. Oops. Okay, so I have answer over 10.256 plus answer over so my chi-squared statistic is 0.0124, okay? So in this case, you know, we look this up. Our p-value is going to be much greater than 20%. It's probably like 99% in reality. Okay, and so we'd say our data does not provide evidence against the hypothesis that wearing glasses and being left-handed are independent. Can we say our data supports the hypothesis that wearing glasses and being left-handed are independent? Yes, no? Well, we say no. We cannot say that it supports the null hypothesis or anything like that. All we can say is that our data does not, we do not reject the null hypothesis. Our data does not provide evidence against the null hypothesis. Because at least the way things are set up, we just assume the null is true, and we can never prove that the null is true. Okay. The only way we could prove that it's true is if we were to survey the entire population and truly find no link between these two things. Okay. Are there any questions on all of this? Is this okay? All of this measuring discrepancy between counts of observed and expected? Okay. And then there's just kind of the natural expansion. So in this case, we did a 2x2 table, but you could have categorical variables with more than 2 categories. Okay. And then you have what's called the R by K table. and it's still the chi-squared test for independence, and it's done exactly the same. Okay, it's just you've got more columns and rows. Okay, so in this case we would have I don't know, here's it. So you have category A, B, and C, and you have X, Y, and Z. And then you have your counts, okay? All right, so this would be the data, and then the expected counts. You have to create your table of expected counts. And the expected counts are found exactly as we did before. Row total, or I forgot how I wrote it before. Row total times column total divided by your grand total, or n. Okay? Your chi-squared is still exactly the same. Observed minus expected squared over expected. And your degrees of freedom is number of rows minus 1 times number of columns minus 1. Okay, but this chi-squared test for independence can be expanded to situations where you have more than dichotomous categorical variables. So it doesn't have to be male or female. It could be male, female, or other, or did not state, or whatever it might be. Okay, and you could see all of this. Trying to think what else I need to cover here. Okay, with when you do have just one degree of freedom, we could create directional alternatives. Let me see if I have that here. Okay, so if you wanted a directional alternative, this only works when you have degrees of freedom equal to 1, so it must be, for independence, it must be a 2 by 2 table. You could have a directional alternative. Okay, and how would we write our so let's say the null hypothesis is let me think of two categorical variables, is having black hair related to having brown eyes. Okay, so the null hypothesis would be black hair, brown eyes are independent. And then the alternative will be having black hair increases the probability of having brown eyes. And symbolically, we could write it this way. Okay, so we could have probability of black hair. Let me change this. Probability of brown eyes given black hair equals the probability of brown eyes given not black hair. Okay, and then the alternative would be probability of brown eyes given black hair is greater than the probability of brown eyes given not black hair. Okay? And then the test would be carried out the same way as before. And it's just at the end, well, you should do a directionality check just to make sure that the data supports the direction of your alternative hypothesis. Okay, so check directionality to make sure the data supports the direction of the alternative, okay? And then test is carried out as usual. And then at the end, divide the tail area in two. If assuming directionality is met. Okay, what do we do if directionality is not met? So if directionality is not met, we can just stop the test and just say we have no evidence to support the alternative. Okay? Okay, so we'll end the lecture there. I want to talk about, this week you have a lab, but it's very different from the labs you've done. It does not involve R. I'm giving you a research article that, well, it's a few years old now. It's from like 2010, I think. Research article that just uses hypothesis tests, t-tests, and confidence intervals. The way you learned them, just very simple. So most research articles, they use much more complicated statistics and tests. And we're, you know, as far as an intro class goes, a lot of our stuff does not cover these things. But this one uses just straight t-tests and confidence intervals, which you have learned. I think there's just a lot of stuff you can learn from the article in terms of the careful process that went into selecting the subjects for the study, how they've done the randomization, how they kind of recorded this thing. And then, and when they publish when they print the results of their tests, they're not in the format that we're used to seeing. You know, we're used to just kind of seeing, you know, I give you like one problem, and then you kind of do that, and you get the p-value, and you write your statement about that, and they don't do that, right? So, so they print the results of their tests, and you know, in a table, and I think it's a worthy thing to see how p-values and confidence intervals are presented in different articles, and this is just one of many, and to be able to look at that table and understand what it's talking about. So so I have some questions about that. I'll post all of this stuff online, but that will be the lab that you'll work on this week and turn in. Okay. All right. We'll see you guys next week.